Pratim, and another colleague, Jack Hansen. So just to tell you the details, it starts on July 11th. So 11th to the 16th, I think, is a mini course that introduces you to first passage percolation.
These are all hybrid, right?
Yeah, these are all hybrid. And so please register online. It's easy to find. You can go to fpp2022.org. It used to be fpp2020.org. Then I had to create a new website. But now finally it's on, and it's going to be in hybrid format at ICTS. So please register online, and then we can send you all the links if you're interested. So register online, and we will send you the links, the Zoom or Teams links. Okay. And the main conference is from July 18th to 29th. So this is a workshop conference. And so we sort of intended to be a conference in the AIM style, where we just have 2 talks in the morning, and afternoons, essentially, we form these little groups where we speak to each other and work on different problems and so on. So very relaxed format. Okay, so last time, just to remind you of the notation, I have a passage time, Txy. I have tau e edge weights on the edges of the lattice in ZD, but for most of this talk, I'll focus on D equals 2. We have a time constant, which was the limit of the passage time, T0 and x divided by n. And I also had the limit shape, which was the level set of the passage time, mu x less than or equal to 1. Okay, so this was limit shape, time constant. Okay, so last time we talked about finite geodesics and KPZ behavior, and we ended with infinite geodesics. And this particular families that we care about, that was sort of guaranteed to exist by the Newman-Leitcher results. I'll draw a picture and show you what these families of geodesics look like. There's one starting from each point on the lattice. And they are geodesics, meaning they minimize passage time between every pair of points on it, and they're all infinite, at least in one direction. So their main property is that once 2 geodesics coalesce or meet, then they stay together thereafter. Then they coalesce. Write it this way. Okay. So in these families, in this field, there's been an old question. And so let me just set up some notation, in fact. So let me call this a compatible family of geodesics if they have this property. Family of geodesics. And I'll call them X sub Z, Z in ZD. Okay. So a very important question in this field is to ask, are there bi-infinite geodesics. This was, I think, originally asked by Furstenberg.
So,
Yeah.
what is the compatible family?
Just this property.
Just the property above.
Once two geodesics meet, then they coalesce.
So if tau e has continuous distributions, then it is automatically, well, when the geodesics are unique. So there's
the geodesics are unique, but the sort of situation I want to avoid is one geodesic going like this and another in the same family sort of crossing it. So I want, at each point, I want a unique vector that tells you in which direction.
I see. So by compatibility, it would sort of enforce some sort of unidirectionality, at least in 2 dimensions.
Not quite. In unidirectionality in the sense that, okay, they might cross a certain set of planes, but no asymptotic direction, for example. That's not
possible.
Yeah.
But here, the notation I didn't understand. X is what? I mean,
so X
is.
Let me write that down. So X is just a map from Z to.
The whole thing is after.
Oh, is that arrow at each point? Is it?
This is not the arrow. This is just a walk at each point, and so it's say maybe x sub 0 is equal to x sub z is, at 0 is z, and x sub z of 1 is it could be z plus e1 or something like that. Okay. So this question of bi-infinite geodesics, interestingly enough, is connected with the Ising model. And let me describe that very quickly. So this Ising model, you have a space of configurations. So configurations. Sigma, let me write it this way. It's plus or minus 1 to the ZD, and sigma in the space, maybe I shouldn't call it omega, but whatever. Sigma and omega is a configuration, or rather a set of spins, some going up and some going down. Plus ones are going up and minus ones are going down. Now, if you fix some finite subset of the lattice, ZD, number of elements in it are finite, then you can define an energy as follows. For these energies, I still use my edge weights tau E, E in the edges of Z2 or ZD, and the energy of this finite subset of the lattice of this configuration is equal to summation minus tau xy or sigma x sigma y summation over x and s, and y is connected to x. Y is the nearest neighbor of x. So in this Ising model, we're usually looking for ground states or minimal energy configuration. Ground states or minimal energy configuration. Okay. So you'll notice that if the spins sigma x, if this is plus 1 and this is minus 1, then the energy becomes positive because these edge weights are positive. And so the overall energy is positive, that's large, but if they have the same sign, minus 1 and minus 1, then the energy is negative. So two clear ground states you can check are sigma equals plus 1 and sigma equals minus 1 identically at every point. So here there was a conjecture or question. So if we call these trivial, the question was, are there any non-trivial ground states? In this random Ising model.
This is still an infinite lattice, right?
This is an infinite lattice.
And S is a finite set thereof.
Right. So I haven't defined ground state. I ignored, I sort of hid that under the carpet, but I can define it. So a ground state is something, sigma is a ground state. If for any other mu, another mu in the set of configurations, we have hs of sigma less than or equal to h mu of sigma of mu, hs of mu for every finite subset of the lattice.
In the case of the Ising model, it's kind of obvious that these are the only ones, right? Because if once you have any kind of boundary.
Yeah, I think so. Yeah, at least this sort of infinite. The Ising model somehow they care about Ising models where you have boundary conditions, these plus or minus signs.
So what are the trivial grounds? With all plus or all minus?
All plus and all minus. Those are the trivial ones.
I mean, ground state, if you condition on the outside, I mean, for the same, this mu and sigma have the same thing outside of S, right? Or do you want to put it this way? Because this way it is clear that the minimizing is all the same.
All the same, yeah, that is what I'm saying. But
yes, so yes, so I would say sigma not equal to mu. That's right. Sigma for any other mu that that differs from sigma on some finite set. I don't know. It could be different from S2, then or only on some finite set. Does that make sense?
I think that's to me.
huh?
I would have thought to ask hs of sigma less than equal to hs of mu for any mu with which is equal to sigma on S complement or something like that. Or not really. I'm not sure. Okay.
No, I think this is the right formulation.
This is the.
I think this is the right formulation. Wouldn't matter.
You
But
look at all the points which are asymptotic to the original one, and you want to minimize the energy for these choices. This is what I remember. But I think even in this case, I think it's just the trivial ones which are.
sorry?
Even in this, with this new definition, I think it's just the pluses and the minuses.
No, I don't think so. I'm pretty sure that it's open, but I'm just a little confused about the definition.
No,
Unless you've solved it.
So I have a habit of saying that open questions are obvious, realizing that they're open.
But let
I
me.
was just talking out of intuition.
Actually, I think the open isn't the precise statement of the open question. Precisely what you said, Nishan.
Yeah, the question is, are there any non-trivial ground states? I think this definition is right because, and I think it might be equivalent to what Manju says too, but I don't know.
No, now I understand it.
So, Madhuna, you were probably thinking about differing outside of a specified S, right?
Yeah, it's anyway, I was just thinking, so this is fine. Yeah.
Okay.
Yeah, if you just look at the set of sides where they differ and you take the boundary of that, your Hamiltonian won't change values if you take a bigger set step, and that's the natural set you take.
Yeah. Okay. So this is an important question, and Newman showed that the following. He showed that.
So there's no probability here, right? It's a simple sort of symbolic dynamics question.
But almost sure, yeah.
Yeah, almost surely no ground state.
Weights are random.
The weights are random.
Oh, right, sorry. What was it? Yes.
So Newman said there are non-trivial ground states. Ground states. If and only if there exists by geodesics in FPP. The proof is the following, loosely. If you have some bi-infinite geodesic, then you have plus ones above it and minus ones below it, and then one can show that the geodesic condition implies that this will be a ground state. So here you assume F continuous. D equals 2, I think. Okay. Okay, so there's very little known about these questions. In the solvable model, it's known that there are no bi-infinite geodesics. There's a theorem of Ware which says that the number of bi-infinite geodesics is either 0 or infinity. So that makes sense just from ergodic theory sort of considerations.
So for the other side, you will somehow look at the boundary between the +1, +2, and -1. Is it if and only, right? It's Newman theory.
Yes, yes. Yeah, and somehow these Hamiltonians are engineered in such a way that it only sees the interfaces of +1s and -1s. At least the differences of the energies. Yeah. Okay, so let me state another theorem.
Rithipratim and Shishindu, did they do something on this? Was it this?
Not Rithipratim and Shishindu, but I think it was Rithipratim, Saurav Sarkar and Chris Hoffman.
Oh, okay.
There in the solvable model, so Newman had the sketch of how one should be able to prove this, and they used all this information about the solvable model to make that rigorous. So it's known in the case of exponential FPP. So in the solvable model, exponential weights, LPP, Basu, Sarkar, Hoffman. I'm not sure if it's Saurav Sarkar or somebody else, but I'll say I remember, and I apologize to the middle author. Okay. In the solvable model, it's known there are no bigeodesics. Okay. There's a theorem due to Lecce and Newman. In D equals 2, assume IID weights. Very important here. And assume we are in a good direction theta. Assume we have a compatible family of geodesics as previously defined in direction theta, then all geodesics must coalesce almost surely. Must coalesce.
Compatible family in direction theta.
Meaning from each point, you look at the asymptotic direction, it's theta.
Oh.
This doesn't have to be in direction theta, it can even just cross planes and stuff like that.
So
Can
when
be,
you
we can.
define compatible family,
Yeah.
you really didn't, you didn't imply that all possible infinite geodesics must have the coalescent property, right? You meant that the family must admit an infinite geodesic issuing from each point Z.
Yes.
And must have the coalescent property.
And just this compatibility property. If they don't need to coalesce, but if they happen to meet, then
I'm
they
so
coalesce.
sorry. When I said coalescent property, I meant provided they meet.
Provided they meet, that's right. And so they could not meet.
So they could if they never meet, they don't need to coalesce.
Yeah.
So I mean, so you can have strictly smaller families than all. Definitely, you don't need the set of all separate geodesics.
Understood.
Then all geodesics must coalesce almost sure. So it's also open to describe what happens when, well, it's not open now anymore. What happens when you don't have IID weights? Don't have IID weights. What happens?
It was open.
Yeah, was open. I'll answer that in a bit, but I just wanted to show you why somehow, if you okay, so let me state another theorem. In this theorem, it says that, or rather corollary, says that under the above conditions, compatible families cannot have bigeodesics. It's a beautiful argument, and it sort of mirrors the Burton-Keene idea. Okay, I'll come back to this if there's interest in this argument, but this is the key. We care about existence of bigeodesics, but in general, away from the solvable model where nothing is essentially known, we can only make statements like this. We say, if we have IID weights D equals 2 compatible families, then by Liccia and Neumann they coalesce almost surely, and that implies that we cannot have bigeodesics. Would you like to see an argument, a quick argument as to why you can't see bigeodesics?
So bigeodesics are just bi-infinite geodesics.
Bi-infinite geodesics.
So IID is important, or is it just finite energy?
IID, you can replace it by finite energy, but you know, finite energy is almost IID.
Almost.
Yeah.
It would be nice to have an idea of how it works.
I will defer that decision on you because I don't know what else you have to offer. So.
Okay.
This I sort of can guess.
Okay. So we showed that every geodesic must somehow coalesce, right? Every pair of geodesics must coalesce. So writing that in terms of probability, we'll get the following. We'll get that that P geo Z1 geo Z2 in direction theta. I could write it as x sub Z1 and x sub Z2.
So I was a little bit confused with the definitions. So the conclusion is the following. So Busemann-Newman's argument says that if I have a compatible family of geodesics in the direction theta, uh, then they must coalesce almost surely.
And if you have IID weights, then
IID weights and D will be equal. And this theorem is about any geodesic. Because so there could be something which is, like, for instance, couldn't you have some sort of loopy thing which does not have a direction?
You could have, certainly, yeah. But all Lecce and Newman's argument, I've said direction theta, but I mean some sort of generalized direction. So as long as it crosses a set of planes, it's still true.
Right, so you have mentioned this a couple of times, so I didn't actually get it. So it crosses a number of planes, you mean?
For example, it crosses in D equals 2, it crosses every vertical line, for example. And in the E1 direction, say.
I see. So if it is infinite, by infinite, then anyways it will do something like that for sure.
Yeah.
Cross means cross and don't come back is what you mean, right?
You can come back, but there has to be a point at which you cross it forever.
Forever. So after that you do not come back.
Yeah, there exists some time at which you cross every plane and never come back.
But didn't you give a theorem last time which asserted that every geodesic has a direction or something? Newman's theorem?
That's Newman's theorem, but it's under the assumption of uniform curvature. So we want to move away from any assumptions on the time constant.
So I just want to, so you're saying that any bi-infinite geodesic will automatically cross all, say, vertical lines in two dimensions?
And no, I'm not saying that. So no, I'm not saying that.
Okay.
Yeah. They are not contained in these families that have a direction for sure. If they have a direction, then they will cross lines. You can check that. Okay. So so the probability that there exists xz1, xz2 in direction theta, which coalesce at x must be positive. So if not by the union bound, they never coalesce, but we've established that all geodesics must coalesce. Okay? A union over x, then that. Okay, so we have these coalescence points. And so really we see that all these geodesics must form a big tree. And now, because this probability is positive, if I call Ex positive, then the ergodic theorem says summation indicator E sub x over x in, say, this box divided by the size of the box goes to this quantity P E0 above, which is bigger than 0. So in a box of size, say n squared, you will have, if nd equals 2, then this means you have p square many coalescence points. So we have a tree, and I'll call the places where this tree sort of intersects the boundary of the box, I'll call those leaves. And then you can show that the number of leaves in this tree must be at least the number of coalescence points. This is a property of trees. Internal points of trees, number of leaves must be at least the number of coalescence points. You can see that. However, the number of coalescence points is n squared p e naught, and the number of leaves is at most 4n in d equals 2. And so this is a contradiction. N is much smaller than n squared.
So this is exactly the Burton-Keane argument.
This is exactly the Burton-Keane argument.
So this also then generalizes to amenable groups quite like straightforward.
Yes, it does. This Burton-Keane argument was actually, if I remember correctly, it's based on this original idea of Newman and Shulman. Okay, so remark, this is quite general. Yeah, needs d equals 2 for the Leclerc-Neumann result to show that things coalesce, and it requires unique geodesics. So and then you needed IID as well. Was needed for coalescence. Needed to show coalescence.
So I'm still a little confused. So the reason is you are saying that if okay, so this is a statement about any geodesic, right? Sum by infinity.
This statement is about these a subset of any geodesic. The general conjecture is that there are no bigeodesics. So you could have crazy bigeodesics, like they say, like you say, like doing crazy things like that.
Right, but somehow this corollary is contradicting existence of those as well in this particular case, right?
In it only talks about bigeodesics in these compatible families, which exists in every
so
direction.
There are no. I see. Okay, I finally understand. Sorry. Thank you.
So this is still quite a ways away from the general conjecture. So if you could show that every bigeodesic had some sort of generalized direction,
compatible family associated to it.
Yeah, and this is sort of what Alborg and Hoffman do, but they can't get all the way because they still need differentiability and things like that. Some properties about the limits. Okay, so now I want to move on and talk about how do you construct these compatible families, or rather a more analytic way of constructing these compatible families of geodesics. So this brings me to the theory of Busemann functions, and I'll introduce them. So if you've found this talk about geodesics kind of confusing, hopefully I can start from scratch and explain at least some small bit about Busemann functions. So given some metric space, x comma d, this is my space and this is my metric. I want to define geodesic rays. A geodesic ray is a map from 0 comma infinity to x such that gamma t minus gamma s equals t minus s for every st and 0. Okay. I'm writing it this way, that's wrong. I should write it this way in terms of the metric. Okay. So all this is saying is that the geodesic ray has been given the arc length parameterization or something. Okay. So you can also think of this as an isometry from 0 infinity with the absolute value to the image of gamma in x. Okay, so then you define, or Busemann defined this function. He said b gamma of x is the limit as t goes to infinity of d gamma of t comma x minus d gamma of t comma gamma of 0. So the first question that should be on your mind is, does this limit exist? So do you think this limit exists in general, if you've not seen it before? So I find it, somehow it's not obvious, right?
Assuming uniqueness or something, is that not needed?
No, nothing is needed.
Oh.
You just notice that this function, if I call this f of t, is bounded and monotone.
You already told me in TR for caps or applications.
Doesn't count.
So you assume that space to be geodesic metric space?
Yeah, uniquely geodesic.
Uniquely geodesic.
Not doesn't matter so much though.
But that is geodesic.
Yeah. This array should exist like this. So you can see, I'll just show you. It's just an application of triangle inequality, so it's worth seeing. So you take this guy, and you notice that this is smaller than or equal to. So I have points x, that's my geodesic, that's gamma 0, it's gamma of t. And then I could go from, say that's x, so I could go from x to 0 and then follow the geodesic from gamma 0 to gamma t. So that will give me an upper bound for this. And I'll write it as b gamma t comma gamma of 0. I go from x to gamma of 0, then I'll get b gamma of 0 gamma of t. I'll just subtract this guy. Gamma of 0. And so that means these two things cancel. So this was ft, and I used triangle inequality on this guy, used here, and I got an upper bound that was sort of independent of t. It's just some number. So I can show, using the same idea, that ft is smaller than or equal to the x 0, and an identical argument shows for s less than t that ft is less than or equal to. So this Busemann function exists.
So the second term actually increases by 1 every time, I mean with t. So with t there, but the first one is kind of at most by 1.
Yes.
It increases to
If it's increasing discretely, yes. Yeah. Okay. So in general, it also gives you this Lipschitz estimate, px minus b gamma y is less than or equal to x minus 1, using similar ideas. So Busemann sort of invented these functions to study parallelism. So let me give you a sort of one geometric application of these Busemann functions. They were originally used, so let me give you an example application, and I'll be imprecise about this. So in Hadamard spaces, so these are complete cat0 spaces. Here you say that Busemann functions, b gamma of x. Let me get the exact statement. It says two Busemann functions are the same up to constants or rather one is a shift term, another by a constant. If and only if limit t going to infinity of d gamma 1 of t, gamma 2, I'll call them b gamma 1, gamma b gamma 2 of t is finite. Okay, so this is these two remain within a finite distance of each other. Finite distance of each other, and so there's sort of generalized some notion of parallel geodesic. So there are many other applications for these Busemann functions, and in fact they're used for compactification in these cat0 spaces and so on. I think I do know the analog of what happens in first or last passage percolation, and it'll be interesting to explore these things. But
so when you say you know what happens, you mean
what the analog of sorry?
What is the boundary of?
Yeah, and in fact, these sort of stationary models, so to speak, in last passage percolation, some sort of compactified version of these spaces. So there are lots of theorems in geometry that maybe could be ported, or you could find analogs of, and maybe you'll say something interesting about first and last passage percolation.
They're probably not just analogs. Probably there's some metric structure on the space under which it's actually the same object.
It is. I mean, we do have a metric space, and these Busemann functions, if they exist, you can use to compactify them using these general theories. But there's also some metric structure on the space of Busemann functions itself.
Which will be like which is precisely like a boundary of your group.
Yeah. And interestingly, there are parallels between the Martin boundary of a random walk and random environment in this theory itself. There are like variational formulas describing it that look exactly like the time constant. It'll be nice to build a sort of a unified theory of these sort of things too. Yeah. Or maybe it's already known and it just has to be written, cast in probabilistic language. Who knows?
There's a statement that the net sum of knowledge in the world is constant.
It tells you that stupidity must also be increasing a lot, right, to offset the increase in.
It doesn't change, right? It's all preserved.
Sorry for getting distracted. I'll get back to mathematics. So, in first passage percolation, V gamma of x, y, omega is defined as limit n goes to infinity of t x gamma n minus t x gamma y. Gamma n minus t y gamma n. And again, the limit exists for the same region, for the same reason, but this quantity has forgotten about the origin or beginning point of gamma. There's no gamma 0 here in some sense. Okay? I've replaced that by y. So this is again like a two parameter Busemann function, or a gradient of a Busemann function, and somehow these sort of definitions help us get stationary versions of Busemann functions, meaning if you shift it, you get the same sort of properties everywhere else, and sort of coming up with these. So by stationary, I mean v gamma x plus z, y plus z, omega shifted by z, shift the weights by z. That's the same distribution as b gamma xy omega. Okay, so why do we need these stationary versions? We somehow want to use the ergodic theorem effectively, and this is one of our big tools in this field. Okay, so how do we produce them? How do we produce these Busemann functions? These Busemann functions in FPP. So here I'll give a sort of microscopic view of this and show where they come up and how they are related to these families of compatible walks I showed you. So it will turn out that if you have a Busemann function, you can construct a family of compatible walks. And once you construct this family of compatible geodesics or walks, then you can ask what can you say about them, and then I'll state that, I'll state a theorem about that, and then we'll essentially be done. I went kind of fast because I wanted to cover this theory about Busemann functions. Was that sort of understandable? Do I need to clarify anything? Okay. And I also forgot to repeat questions to the online audience, so please stop me if
is there any overview type of a reference for Busemann functions and related stuff?
Yeah, sure. There are many reviews now. There are many reviews now, and it's sort of a standard topic in metric geometry, and yeah, there's also big words associated with it. It's like you can use these Busemann functions, the Gromov boundary or ideal boundary of these metric spaces, and it's some big field. So I can send you references after the talk. I'll send you
sure,
a couple.
That'll be great. Thank you.
For hyperbolic groups, Calgary has a nice book.
Calgary has a nice book.
Yes, notes.
Notes.
Selection skills.
How do I spell that?
Yes. It's only for hyperbolic groups, not Y, but I. I think it's an I, yes.
Yeah, somehow I don't have enough intuition of these subjects.
Me neither. So
It's like looking at some geodesic,
Mhm.
and then I'm looking at least this co-cycle version of your. Anyhow, maybe after I need to think about that.
Okay.
Are we taking a break at all or not?
Coffee has not yet come. Maybe we can continue till it comes and then take a break.
Okay. So let me do some sort of explicit computations to so that at least the students will not feel that time is completely wasted. So I'll show you how you get geodesics from Busemann functions. Okay? And so to start with, I'll take a finite box and I'll put some weights on it and show you exactly where these Busemann functions come from. So I'm going to have vertex weights, and I'll talk about FPP where paths are only allowed to go up and right. So need one more. Oh. Four. And so let's put some vertex weights down. 3, 5, 6, 4. Okay, so I didn't want these, and I want 1, 4, 2, 3, 0, 3, 7, 9, 1. Uh-oh.
No, same problem.
Yeah, it just crashed. I'll try to open it again. Um, mm. Okay, thanks for coming, Gautam. I do. I'll send them.
Upload them all.
All the videos are so far uploaded in our IIC YouTube channel.
And notes also.
Notes I link it on this session.
Also, I think Yogesh will put everything in the APS website and local designer. He's very organized. Any time to manage, I always say that. Is it a good time to take a break?
It has come.
I can. Let me finish this. I've started, so I'll finish. As we say. Let me just finish this example, and then we can take a break.
It's okay. I just wanted to check if it's there.
391, and there's 1, 5, 2, 3. Okay. And so I'll make a copy of this.
So what are those numbers?
These are the weights,
Weights.
vertex weights. And now I'm going to just form the passage times here. So, of course, you have takes travel time 3 to go there. To go here, it's only 8 because that's 3 plus 5. To go here, it's 4. But to get there, I should take the shortest path. So I should really, this should really be 4 plus 4, that should be 8. 8 plus 6, this should be 14. 14 plus 4, that should be 18. Now I look at both these neighbors. 8 plus 2 is 10, but 14 plus 2 is 6. So this is the 2 I'm talking about. And so this should be 10 because I take the shortest path, and so on. I should keep going. So this will remain 4. Then 4 plus 3 will be 7. 4 plus 1 will be 5. And then 7 plus 5 is 12. Plus 5 plus 5 is 10. And so on. So I'll just finish this. Keep going. This should be 10. And let me just do it. 10 plus 9. 9 plus 7 is 16. Here I have 10 plus 3 is 13. 13 plus 1 is 14. And 13 plus 1 is 14. And then 10 plus 2 is 12. And then 12 plus 3 is 15. So that tells you that this is in fact the passage time from this point A. So you can call this Dijkstra's algorithm. But it's much simpler because I have directed path. So it's a well-known shortest path algorithm. Okay, so now using this, I can reconstruct my geodesics from every point, the shortest paths from every point, and I'll show you how. So what you do is you look at which neighbor has the smaller passage time, and so you must have come through there. And because 14 plus 3 is 17, you couldn't have come through there, so I just draw an arrow in that direction. Similarly, you draw another arrow there. Here the arrow goes this way. Here the arrow goes this way. Arrow goes here, 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 here. This goes this way. at 14 I should go this way.
Is it reversing whatever you did earlier?
Yes, I'm just reversing whatever I did, but I can only do that once I construct the passage time. Okay, so now if I wanted to find the geodesic from this point to the origin, I just follow the arrows. Okay, so it's quite nice. I'll notice something else. Copy and paste this. And you'll notice that I don't really need the passage times. I can just replace that with differences of passage times. Wait, let me not do that. Here I can write, say, I'll write that in green as well. Here I can write 3. Here I can write 1. Here it's minus 2, 14 minus 16 is minus 2, 14 minus 13 is 1. 2, minus 4, 9 plus 6, 17, 3, 5, 1, 0, 1. This is 4, and this should be 0. That should be 2, and this should be minus 4. And 13 should be minus 5, and there's 3 there. And I think I've gotten all differences, 4 plus 6, and so on. Right? Here there's a minus 1, here there's a 3, and so on. I think I've gotten everything. Okay. So how do you construct these arrows? So all I'm doing is I look at these two numbers at this point, and I'll choose the one which is larger. So these numbers that I have, if I erase the rest of these numbers that I've put on edges are just differences of passage times to the origin. So let me write down at least one of them. So if this is A, this difference is T A comma B minus E1 and so TAB minus TAB minus E1, and this one is TAB minus TAB minus E2. E1 and E2 are the unit directions. So now it's enough to have this vector field now at every point. These form our Busemann functions. Okay. So you'll notice a couple of things. So let me write. These will form our Busemann functions. In fact, these passage time differences are Busemann functions. Of course, I have a finite guy there.
Finite.
So I'll have to go after it.
For this metric.
For this metric. For this metric space, yeah. Okay, so to summarize what I had written, I should say.
Construction, the way you're constructing it's like it's because of Busemann function, right? You're
Yes.
subtracting.
Yes, by construction essentially. Now these infinite geodesics are hidden in this construction, but it's much more analytic and local, and so you can make it work in general. And you can get stationary versions also. Okay. I should say this is argmax, as I noticed, was Tx minus EI for I equals 1, 2. This is the arrow, those green things I drew. And the other thing is that the max of T, say x minus Tx minus EI, I equals 1 comma 2, just gave me back the weight there. For example, this gives me the weight at x. So just to show you, if I look at the max of these two numbers, 3 and 1, the max is 3, but that's the weight here. That's no coincidence.
It must have come through that.
Must have come through that. Right? And so this is a local property that defines these Busemann functions. Okay, no global geodesic needed. So there's another way to view this property, and I'll write it down. Suppose my origin is here. I want to get to the point X, but I can get to the point X from one of its neighbors. So I must come through X minus E1 or X minus E2. And so it's clear that T0X is the minimum of T0 X minus E1, T0 X minus E2 plus the weight at X. I shouldn't write omega, I should write tau sub X. And this is called a dynamic programming principle. Okay, so I'll stop here. We'll take a break here, and then we'll come back, and I'll show you how to construct these Busemann functions and
So you have a
what
dual
we.
problem there or something?
Sorry.
Do you have a dual problem with this?
Dual in what sense?
Because this is some kind of dynamic optimization.
Dynamic programming, yeah, not at the local level, but you can extend this dynamic programming to a variational problem for the time constant. That will have a dual formulation. And at the local level, I don't know. Maybe there's something, I don't know.
Maybe not also. Thank you.
Shall we take break?
Yeah, we'll take a break.
Okay, we'll come back maybe in 8 minutes.
We'll come back in 8 minutes.